All right, so for today's lecture, the last lecture, we're going to talk about SIMS, or secondary ion mass spectrometry. So this is another surface sensitive technique that we talk about in connection to AES and XPS. And so the first module, we're going to talk about the basics of this SIMS technique. All right. So SIMS, or again, secondary ion mass spectrometry, is related to sputtering. We saw sputtering involved in XPS and AES. We also saw it in somewhat connection to SEM when we talked about surface coating. This is where we use an ion beam. So this is our primary ion beam. And we aim that and direct it at a surface. So this is our sample surface. And by doing that, these high energy ions cause a lot of interactions and cause particles to become ionized, and we get secondary ions from the surface that are basically liberated, and we use those secondary ions to identify and determine what's in this material. And because we can control the ion beam, we can control just the surface. And so that's what gives us the surface technique of this. Also, the fact that we're able to constantly remove sample means that we can also do depth profiling with this technique very easy. Sorry about that. And so that's something that we use here. Just a note though, when we have the collision of the ion beam with the surface, we get secondary ions. So again, particles from the surface that become ionized, but we get a lot of other stuff too. So secondary ions are only a portion of what we create, and we'll kind of talk about what those other things are. But basically the idea of this technique is we produce these from the surface, and then we use a mass spec to analyze the masses of these ions, and that gives us composition. So it's basically sputtering plus mass spec, and that gives us the connection, and that gives us the ability to do composition. All right, and so some of the reasons we choose SIMS as opposed to other techniques or in conjunction with other techniques is because it gives us some things that we can't get in other techniques. First of all, it detects hydrogen, and that's a big one. We talked about some of the techniques like SEM, EDS, for example, and then also XPS, AES. Those don't work for hydrogen. Hydrogen's our lightest element, and it's very difficult to detect. But SIMS is one of the few techniques that we can actually use to detect hydrogen. So basically, we have the ability to detect all elements, which is powerful. Another thing is that because we are looking at mass, then we are able to differentiate isotopes, and so we can use this technique to detect various isotopes. And the other, some of the other things that go along with that is that the detection limits are very low. So with XPS AES, we're talking about 0.1% EDS and things like that. We talked about having a pretty high detection limit, but we can detect as low as 10 to the minus 6 percent of elements in SIMS. So we can detect very low concentrations, and so that can be powerful in certain techniques and certain applications. And the other obviously is that it's very surface sensitive, so it can be a nanometer or less, and so that's useful. So we can detect just 1 or 2 atomic layers on the surface. So all of these make SIMS a really powerful technique that gives us a lot of additional things that other techniques struggle with. All right, so there's a couple different modes of SIMS. The first is dynamic. And so this is what we would term a destructive process. And it's useful because we are sort of destroying the surface, but in doing that, we're able to depth profile. And so the way we sort of classify dynamic SIMS is by the ion flux and therefore the flux density. So the primary ions, those ions coming in, have a flux of greater than 10 to the 13 ions per centimeters. And so that works out to be, you might see it as a flux density, and that's greater than 1 microamp per centimeter squared. So just basically a different version of the same one, kind of using electronic terms as opposed to ions. And so this dynamic SIMS removes many layers at a time. And so obviously this is good for depth profiling when you're trying to get what the surface looks like, then what the next layer, and then so on, because it's removing a lot of layers. And it tends to occur over a relatively large area on the surface. So this technique, it's destructive, but it does have its application in depth profiling. All right, so with that in mind, we talked about dynamic SIMS. So you can imagine there's something called static SIMS. And so static SIMS is termed non-destructive, right? But I've also talked to you just now about what SIMS is. So with those two ideas, what SIMS actually is and this static SIMS, which are terming non-destructive, how can we sort of reconcile those two different ideas? So how is this possible? See if you can come up with an answer, brainstorm this a little bit, pause the video and go answer this on the weekly quiz. All right, so now that you've had a chance to look at this, the idea of static SIMS being non-destructive, but what we know about SIMS, let's see if we can reconcile these two things. So we define static SIMS based on we are destroying or sputtering, but it's a really small area. And so we can term it non-destructive because it's non-destructive to the bulk material, because we're only damaging a very small part that doesn't affect the bulk material. So it is still sputtering, destroying the surface, but it's doing such a small area that we term it non-destructive. So this is very similar to something like hardness testing. Typically, hardness testing is considered non-destructive because it's only indenting a very small portion of your surface. It's not affecting the bulk properties. And so that's the same logic we can use here. So technically it is destroying the surface, but it's a very small area. And so typically these areas are less than 10 nanometers squared. So very small areas that we're looking at. So we define static SIMS based on that, but also, again, by the primary flux. So in this term, it's less than 10 to the 13 ions per centimeter squared, and that's results in a flux density of in the order of 2.7 nanoamps per centimeter squared. So you can see nanoamps is very small. And therefore, less than 1% of the surface atoms are actually bombarded. And so it's still going to be considered non-destructive because the rest of the material is unfazed. So that's how we can get around the definition there. All right. So as I previously mentioned, this primary ion source that we have induces sputtering. And sputtering is that ejection of these secondary particles. And some of those secondary particles are secondary ions. And so that amount is about 1% of those particles that come off are ions. The rest of them are either neutral, they're atoms, molecules, or they can't even be electrons. And so it's a very small amount that we're actually getting. But this 1% is what we're interested in for this SIMS technique, because again, we're looking at secondary ion mass spec. So this primary beam, if you're wondering what it is, we can use a range of ions, but some of the more common ones are argon, gallium, and cesium. And so that's the primary beam that comes in to initiate the secondary particles. And so the interaction is what we're going to talk about next. So this primary beam, how it interacts with the surface to actually cause the sputtering, because there is obviously a simple interaction of the primary ion hitting the surface, and you get what's called a 1-to-1 knockout, right? One ion causes the emission of one particle. But actual interactions tend to be very much complex, and so we want to talk about that in the next section here.